Can you see now?
Yeah, but it's not in full presenter mode yet.
Okay, wait. Now it should be seen, maybe.
Yes, perfect. Okay, now we have Seyma Mercimek talking about formaldehyde deuteration in a protostellar cluster with ALMA. Go ahead.
Thank you. Hello, everybody. I'm Seyma Mercimek, PhD student at Archet Observatory, Florence, in the context of the European Horizon 2020 Network ACO. First of all, I would like to thank all the organizers to give me this opportunity to present this very nice ALMA preliminary results. So generally, my interest is to build up a chemical census of low mass star formation from class 0 to protoplanetary disk to make a comparison in terms of the chemical evolution, focusing on complex organic molecules and deuterium fractionation in order to see if there is the inheritance scenario moving from the early stages to small solar system bodies. So during the next 15 minutes, we try to get some hints to understand if the water in oceans comes from either comets or protostar nebula, which are sun-born. So I would like to take your attention why really we care about the deuteration. So one of the way to understand the chemical evolution of the interstellar gas on our planet is to measure fractionation here between column densities of deuterium with respect to the hydrogen in the molecules, as we called deuteration. So deuterium-bearing species are kind of powerful key to investigate the chemical evolution from the past to present. So mainly the deuteration process of the molecules are stored onto dust mantles and released into the gas phase when, of course, temperature is high enough to evaporate grains. So D over H values are referred to be kind of fossils of solar-like star forming process. So to give you a very basic idea, and deuterated water here is more heavier than water. So it gives less brightness in the spectrum. So the fractionation between these two molecules can give us an idea how chemical evolution changed from beginning to now. So below you see here deuterium fractionations of water as a function of time during the low mass star forming process. So what do we care about? The fractionation on water abundance of deuterium is about, here you see 10 to minus 4 in the Earth ocean, while this number is 10 to minus 5 in the interstellar medium, basically is set by Big Bang. So it is this 10 times larger than cosmic abundance, obviously. So we want to understand really where water in ocean come from. So the strong evidence here is, you can see with the comments values, comments brought water to the Earth. So however, the values here, as you can see, are not exactly the same with the ratio on Earth. So to reach maybe the real answer or final answer, we should also look the other deuteration of other molecules. So here in the plot, you see three abundance ratio with respect to the their main isotopologue during the low mass star forming process from our previous work. So before the break, thanks to Teresa, she explained us evolutionary stages in low mass star formation from core phase to class 2 phase, which we can see a naked protostellar disk. So I can directly dive into the comparison. Here in the plot, you see the ratios of formaldehyde, methanol, and thioformaldehyde from the literature that we also studied here for class 1 protostars in terms of the ratios with IRAM single dish data. So it seems that the deuteration from prestellar core phase to comets here, for instance, for the methanol, is likely constant. So generally speaking, These results are supporting that D over H value set in the protostellar curve phase has been inherited by the later stage of star forming process. To really test this scenario, because half of these points from single dish data, either from single dish data or relatively low angular resolution interferometric data, we need definitely high spatial resolution observations with high sensitivity. Since I told you deuterated species are less brighter than hydrogen version of a molecule, so for this we need also a large number of sample for the better statistic. So definitely we need ALMA. For this reason, at this point, FAUST ALMA large program arrived to improve our knowledge on the deuteration case. So the aim of this large program is to reveal and quantify the variety of the chemical composition of here you see the envelope disk system at roughly 50 AU scale, where planets are expected to form. And we are working on the class 0 and class 1 protostars. So the FAUST team is focusing on not only deuteration, but also molecular complexity and gas ionization. Here using this tracer listed here, using 30-meter and 7-meter ACA configurations. So for our project, because we now can disentangle structures in protostars like outflow, inner envelope, disk, host corino, etc. So we can make a systematic work on the deuteration, focusing on these different regions. So here in general, you see we have 13 class 0 and class 1 sources and located in relatively nearby molecular clouds. Also, you see the highest angular resolution that we could reach with ALMA FAUST program. So today I will show you some preliminary results towards VLA1623A class 0 protostar. So this source is not only a single point source, is a kind of is a protostellar cluster located in Ophiuchus. Consists of here you can see the class 0 sources with source A and source A1, A2, and here source B. They are all class 0 sources. And we can see them separately with a continuum emission from Harris 2018, which is another ALMA work. And also there is another source, which is called source W, showing edge on disk class 1 protostar. So with FAUST within 50 AU resolution, we are not able to disentangle to separate source A1 and A2. So that's why, after all, I call them just only source A. And here in the sketch, you see the how complex structure is. The collecting all the information from the literature showed by another FAUST work by Satoshi 2022. And you see here A1 and A2 derive jets, and these two sources surrounded by a circumstellar disk. On the other side here, you see source B has also a jet with the rotating disk structure, and these three multiple systems are covered by a circumbinary envelope. With FAUST 3, we showed outflow cavity wall driven by source A with CS emission. You can see several channel maps from the structure. And we also see extended rotating disk with H13CO plus emission covering source A and source B. So in the context of deuteration work, I am examining 3 species, which are formaldehyde, and its single and double deuterated forms in this system. And today I will show you some preliminary results on the structure, what we see with formaldehyde and its deuterated sisters. So here on the left in the moment 0 map, you see the dashed line, which represents outflow cavity location from FAUST 3 results. So we see that also formaldehyde is tracing outflow cavity wall. As a plus, we see some accretion streamers which also Hishi 2020 reported with C18O and SO tracers. So following to their streamer findings, we also obtained here some moment zero map selecting spatial velocity range, which is agreement what they reported. So we could catch western here and southern streamer, as I called kind of frog legs. So in addition, we also see some other northern streamer on the right, moment zero map, creating onto source A. So we are going to examine these streamers more in the next days. So in the same sense, this time you see here two HDCO maps in different upper level energies. So we can see that here on the top, the less excited line is tracing more extended outflow cavity wall with well-defined X shape, while a higher excited line here in the bottom tracing more compact region. But it's agreement to see again this outflow cavity wall. In the channel maps of these two HDCO lines, also we see two different regimes: rotating inner envelope or disk structure in 50 AU scale. Here you can see. Also in the bottom, as I told you before, we see outflow cavity wall. As you can clearly see that in both regimes, the higher excited lines traces more compact gas, and less excited line traces more extended gas. And finally, we could get double deuterated formaldehyde, which is D2CO. As you know now, more times of deuteration means the more less chance of emission. So luckily for this source, we could have able to have DTCO emission. Here you see, just to make it clear, I show you double deuterated formaldehyde in a color scale, overlapped with a single deuterated form with black contours, pointing out that the both the DTCO and HDCO are following the outflow cavity wall.
3 minutes.
Okay. After all analysis that now we know that these three species trace outflow cavity wall as a common structure. For the first attempt, here you see on the right the overlapped emission of three species. So I selected one right position, indicated with the red point, and I performed this analysis along the whole cavity. For example, at this point, I extracted spectra and integrated for three species over the same velocity interval. And from this flux, assuming, of course, LT optically thin emission and temperature range between 30 and 70 K for outflow structure, I derived column densities here, as you can see in the first row of the table. Here, I compare with IRAS 13993, well-known class 0 protostar results from the ALMA Peel's work. So they have a large number of formaldehyde lines with the different isotopologues, so they could derive opacity currently. So even for our case, for the outflow cavity, maybe we could expect the opacity effect could be less than the center of the core, which the PS results are from the center of the protostellar system. Still, DTCO and HDCO ratios over formaldehyde could be upper limit for our case because the thickness of formaldehyde. So for this reason, I also get a DTCO over HDCO ratio, which seems less affected by the opacity and comparable to PS results. So in any case, we compare our ratios systematically with the other values in the literatures on the left. You see plot adapted from Bianchi et al. So we see that our DTCO and HDCO ratio values in blue and black stars are in agreement with other ratios in class 0 sources. So next step is to obtain the values for the center of the VLA source to see how the results could change. And lastly, I would like to tell you about the transversal projects on the deuteration with this wonderful ALMA data. I told you in the beginning, we need more ratio values from different evolutionary stages and structures. So for this reason, I am working on also other two multiple Faust sources, which are L1551 IRAS5 class 1 source is binary system. And here on the right, you see ERCRA IRAS7B, which is the more complex class 0 source. So we are hoping to release the ratio values with the whole structure around like 10 sources totally. So here I am finishing, and I would like to thank you for your attention.
Thank you very much. Very interesting stuff. It's a lot of things that we can learn from iteration. Very nice. Are there any questions yet in the chat?
So, not in the chat, but I have one, so if I can ask. I have a couple, but I will start with one while people write questions. So very short one, just curiosity. So do you also have detections of deuterated methanol, but double deuterated or triple deuterated?
For VLA source, we have no deuterated methanol.
Okay, that's a pick. And well, people are writing, so if I have some more time to ask another question.
Please go ahead.
Yeah. So do you expect that the deuteration level is mainly determined during the core collapse phase or so?
Exactly,
or do you expect that the outflow may also have some effects, or feedback from the star may have an effect on the deuteration process, or just the collapse phase?
Okay, this is a bit speculative still, because in the protostellar core phase we expect more deuteration, and then maybe a bit less towards the later stages. But if we say that outflow structure affect the formation of the stars, we should expect to see some maybe a high deuteration, because we know that from the age of the kind of external core, we can still see high deuteration. So if this can be happen, then outflow, the external outflow, can also affect the fractionation in the system.
Okay, thank you. So there is one question in the chat. Do I have time?
Yeah,
okay.
we still have time for.
Yeah, so hi Seyma, I'm wondering whether there are kinematic differences in different deuterated species. For example, when you integrate over the same velocity intervals, do you for sure know that there are no velocity shifts based on the different species?
Okay, for VLA1620, I can just talk for now. We didn't see any different structure between HDCO, single deuterated and double deuterated forms, but we see some absorption feature towards source A and source B, which can be the optically thick effect. So this is going to be actually our next step to understand the kinematics better, but we don't see any shift between two deuterated species.
Okay.
Or differences.
Yeah, thanks. I think this answers the question.
Okay, are there any more questions in the chat?
Not in the chat for the moment. Yeah, okay. Yeah. Thank you. So the chat is thank you.
All right. Well, maybe there will be more on Slack. Otherwise, I think we can move on. Thank you very much, Seyma. That was